Okay, it's Brian, and we're back for day 2 of talking about lenses and images. Let me start with a quick overview as to where we are in the class. So this week we're talking about lenses and images. Today is lenses and images part 2, and then Friday we're going to talk about the optics of the eye. That's like one of my favorite topics. I really like that one. And I'm leaving the third week, the last week of classes for review. So these days we're basically going to take everything that we've learned and try to put the big picture together and say all the stuff we've learned in this second semester course. Let's see what it lets us say about the world, and we'll do a whole bunch of kind of like problem solving, putting the pieces together. And the whole point of this week is as a chance for you to do some review. It's some review of all the material you've learned, because we will have a final exam, and the final exam will be comprehensive. And this material is naturally comprehensive. It naturally kind of like builds on itself, so that's going to work out well. Quick reminder, you do have a homework due on Friday. Speaking of Friday, on the class on Friday, I'm advising you to have your glasses. If you wear contacts, get up in the morning and look at the video before you put your contacts in, because being able to remove your vision correction will be useful. And I'm going to be talking about the optics of the eye, the truth about Piggy. And remember I said nearsighted people have superpowers? Oh yes, we're going to talk about that. I want to remind you that it's something in the chapter. We talked about the fact that if I have a converging lens, it brings rays of light together to a focus. So parallel rays come in and they go through a focal point. But it's also true if I have rays of light that emerge from a single point and they go through a lens, they emerge out of the lens parallel. And you've seen this before, because if you have a flashlight that has a light bulb, the light bulb sits at the focal point, and so the rays of light that come out of it are essentially parallel. Now I want to talk about mirrors. Last time we talked about images made with lenses. Today we're going to talk about images made with mirrors. We're going to talk about a converging mirror, and a converging mirror brings rays of light together. And so if I have parallel rays of light that come into a mirror, they converge to a focal point, they will also make images. And we're going to locate the image from a converging mirror exactly as we did from a converging lens. We have the 3 special rays. So a ray of light comes in parallel to the optical axis, hits the mirror, goes through the focal point. Ray of light goes straight through the center of the lens and emerges at exactly the same angle as it came in at. Oh, that was a terrible drawing. Comes into the center of the lens and then emerges like so. And then I also have a ray of light which goes through the focal point and it emerges parallel. And all those rays come together to form the tip of the image. So the process we use is exactly the same. The only thing we've done is we've added a reflection. Instead of the rays continuing through the lens, they bounce off the mirror. Now I want you to take a look at this picture right here. So here's a woman, and this was a picture taken by a woman taking a picture of her hands in front of a converging mirror. And my question is this: what is happening in this picture? Which one of these is a real hand and which one is the mirror image of her hand? I want you to take a minute and think about that. Well, here's what's happening in this case. She took this image in a converging mirror. And this hand right here, this hand, this is her actual hand. Because think about this. She's holding the camera right here and taking a picture of the back of her hand. That's what's happening. The other hand that you see, this one right here, is the mirror image. That's the image of her front of her hand in the mirror. And she has just taken the image of her hand and put it so that it overlaps the actual position of her actual hand. So the image and the object are basically in the same place. But this one is real. This is the object. This one is an image right here of her hand, a real image of her hand. And it's very, very cool. And I finished class last time with a version of that photo that I had recreated. And I want to start doing some work with mirrors as we did for lenses. I want you to draw a picture, draw a ray diagram that shows the image for the following situation. 2 centimeter tall object, 40 centimeters in front of a converging mirror with a 20 centimeter focal length. And you want to locate the image position, its orientation, and its height. And we're going to start by drawing the picture. So I want you to pause the video. I want you to draw a picture. I'll be back. Well, the first thing you do is you draw the optical axis, and then I'm going to draw the, well, that was a pretty lousy optical axis. Let's draw more of a straight line. There we go, optical axis. And I'm going to draw my mirror right here, and it's a converging mirror, so I'm going to draw with a little bit of a shape like that. It's got a focal point that is 20 centimeters from the mirror. The object is 40 centimeters from the mirror, so I've drawn that approximately to scale. And then what we're going to do is we're going to draw the special rays that we do, okay? We're going to start with a ray of light that goes parallel to the optical axis, and then it goes through the focal point, like so. And then I'm going to draw a ray of light that goes through the center of the lens and emerges at exactly the same angle, so it's like so. And then I can draw a ray of light that goes through the focal point and then comes out parallel to the optical axis, like so. And it seems like they come together right here, so my image should be right there. And what my ray diagram is telling me is that I think the image is at the same place as the object. And it's inverted. That's what I'm expecting to see. But now what we want to do is do the numbers. So we're going to do the numbers. So same story, 2 centimeter tall object, 40 centimeters in front of a converging mirror with a 20 centimeter focal length, calculate the image position and height. And we'll do that using our basic relationships, okay? And we're going to start with the first one. 1 over, I'm looking for the image position height, so I'm looking for 1 over s prime. But 1 over s prime is equal to 1 over f minus 1 over s. That's 1 over 20 centimeters minus 1 over 40 centimeters. And I use my fraction foo to calculate what that is, and I get positive 1 over 40 centimeters is 1 over s prime. So s prime is equal to 40 centimeters. Oh, heavens to Betsy, that tells me the image is approximately where the object is, because the image is on the same side of the mirror as the object because there's a mirror reflection. If I calculate the image height, I'm going to use this relationship right here. H prime is equal to h times negative s prime over s. Well, s prime and s are both 40 centimeters, so this just turns into 1. H prime is equal to h, except there is a negative sign here. And so I'm going to get h prime is equal to negative 2.0 centimeters. And so what I'll do is I'll say the image is 2 centimeters high, but it's inverted. That's what the negative sign is telling us. And so the calculations that we did basically mirror, oh gosh, made a pun, did not intend it. I'm not a huge fan of puns, so I apologize for that. Anyway, so we do this little situation here. Here, the results that I get mirror nicely the results of my ray diagram. The image was basically at the same location as the object. By the way, too, this is the same sort of situation that we saw in that photograph. She placed her hand so that her hand was at, the image of her hand was at the same place as her actual hand. So the image and the object are at the same point in space. Now I want to talk about a diverging mirror. For a diverging mirror, it takes the rays of light and spreads them out, and we can locate the image. And the image is going to be on the back side of the mirror, just as it is for a plane mirror. And what we do is this. If I have a diverging mirror, just like for a diverging lens, the focal point is on, the focal point isn't a real focal point because the rays of light come in and they diverge. But if I trace them backwards, they appear to come from this focal point. So we're going to find the focal point just like we do with a diverging lens. And I can locate the position of objects. And there's 2 special rays that I use for this. One special ray I use is one that comes in parallel to the ray, to the optical axis. Then it goes out at an angle that if I trace it backwards, it goes to the focal point. Or I have a ray which comes straight in, comes off at the same angle, and if I trace that one backwards, you can see where the 2 rays of light come together, and that is plenty to locate the position of the object. Now I want to notice this. Basically, because of the way that things are oriented, any image is going to appear to be closer to the mirror than the focal point. So basically it compresses the whole world and makes it exist within that tiny little range. There's a classic scene in Jurassic Park, the first one, where Jeff Goldblum and his compatriots are in a van. They're being chased by a T-Rex, and Jeff Goldblum says, "Must go faster." And then the driver looks in the rearview mirror of his Jeep, and what he sees is this. Here's the image of the dinosaur, and it looks like it's pretty close, but then you have the little annotation on the mirror, and it says, "Objects in mirror are closer than they appear." And you've seen this before. You've seen this indication on mirrors before. Now, typically, it would be on the passenger side mirror, not the driver's side mirror, but we're giving Steven Spielberg a pass on this because it did make for an awesome little sight gag where you see this dinosaur, and it says, "Objects in mirror are closer than they appear." Ha, 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 because it already looks like it's pretty close. Anyway, let's do a calculation for looking in the rearview mirror. And it turns out the rearview mirror on the passenger side of a car is typically a diverging mirror. And the reason is, well, we'll come back to the reason. We'll come back for the reason for it. It's a diverging mirror. And a typical number for it is that it's got a power of negative 1.5 diopters. If you look up specifications, that's what you get. So the question is this: where does the image of the dinosaur appear to be if a dinosaur is 10 meters from your Jeep? Where does the image appear to be? All right, so let's do a quick calculation. Oh, but of course we're not going to start with a calculation, you little scamps. You know what we're going to start with, is we're going to start with a ray diagram. So here's my optical axis. Here's my mirror, and it's a diverging mirror, so I'm going to do it like so. And it's got a power of 1.5 diopters, okay, negative 1.5 diopters. Well, remember the power is equal to the 1 over the focal length. So what that tells me is the focal length is equal to 0.67 meters, and it's negative because it's a diverging mirror. So if I extend my optical axis out a little bit, I get my focal point is negative 0.67 meters. It's right there. My dinosaur is out here, and I can't draw a dinosaur very well. Oh, what the heck, I'll try. Let's see how this turns out. That's my dinosaur. I'm going to make it say rawer so that it looks like it's more of a dinosaur. Okay, so there's my dinosaur out there, and we're going to take this as the little point on top of the dinosaur's head that we're going to use as our point on the object. Let's use our special rays. One special ray is one that comes in parallel to the optical axis. When it gets to the mirror, it goes off at an angle so that if I trace it backwards, it goes to the focal point. So it goes like this. The other one is a ray that comes in straight to the center of the mirror and bounces off with at the same angle, and I trace that one backwards. So I'm seeing, holy moly, I'm expecting a teeny weeny little dinosaur right here. So it's going to be really, really small. And the distance from the mirror is going to be almost the focal distance. It's going to be very, very close to the focal point is what I'm expecting. So that's what my calculation shows me. Or I'm sorry, that's what my ray diagram shows me. Next up, let's actually do the numbers and see what we get. And if you do the numbers, we use our basic relationships. And our first one is that 1 over s plus 1 over s prime is equal to 1 over f. And as usual, I'm looking for 1 over s prime. So I get 1 over s prime is equal to 1 over f minus 1 over s. Now notice this, the focal length, 1 over f that appears in this equation, this is the power, because 1 over f is the power. So I'm just going to put in negative 1.5 for this. And 1 over s, I'm going to keep it in meters, because if I'm using diopters is 1 over meters, I have to keep this measurement in meters. So I'm going to get negative 1.5, and then s is going to be 10 meters, and I can calculate a value for s prime. And I think you can see just kind of like quickly, 1.5, this second figure is going to be 1/10, and so it's not going to be very appreciable. The number for s prime will be close to f. If you complete the calculation, what we get is this. S prime, that's the location of the image, is negative 0.62 meters. Okay, negative 0.662 meters. And that is almost where the focal point is. And it comes out with a negative sign, and the negative sign just tells me this. Negative sign tells me that it's on the back side of the mirror. It is not a real image, it is a virtual image. And the magnification negative s prime over s. Since s prime is negative, it will be upright. It will be upright. But if we calculate the magnification, it's also a really tiny number because s prime is tiny, s is big. It's 0.62 meters, okay, for s prime, and s is 10. And so I end up with a very, very tiny magnification. And so I end up with an itty-bitty dinosaur, and the image appears very close to the mirror. Now it's the smallness that I want to consider right now. Since the image of the dinosaur is really tiny, so I get this like giant dinosaur out here, and I get the image of it, which is really, really tiny in the mirror. Since the images are so small inside the field of view of the mirror, and since it's a virtual image, everything that you're looking at, you have to be looking at the mirror. So you only get a certain size. So think about the rear view mirror on your car. Your rear view mirror is a certain size. Everything that you see, all the images have to fit within that circle. So as a consequence, I want the images of things to be really, really small so that I can fit more of the world in. That's the whole point for having a diverging mirror. Now think about this, what the annotation on the mirror said. It said objects are closer than they appear. Objects are closer than they appear. And that's not quite right because the image is closer than the object. So the object is actually farther away than the image. But what it means is this. If you see an itty-bitty image of a dinosaur, you would assume that it's really, really far away. But it isn't really, really far away. It's just that the image is small because it's a diverging mirror. So I think we need to change the annotation on mirrors to make that more clear. And it should say this. This is a diverging mirror, so the image distance is less than the object distance. Nonetheless, your brain is likely to interpret the small image size to mean that the object is more distant than it actually is. Ultimately, you may be led to think that the objects are further away than they really are. And I think we should replace the mirrors with, or the annotation on the mirror with this, because that's actually physically correct. Sure, it's going to block everything that you're trying to look at, but I think that's a sacrifice I'm willing to make to actually be physically correct. Now I want to talk about how to make cameras, and I'm going to talk about the simplest possible camera, which is this. I take a light-proof box and I make a hole in it. And a hole actually will make an image in the box, and the reason is, you can kind of see from here, if I take rays of light from my tree, any ray of light from the top is going to hit the bottom of the screen back there. Any ray from the bottom is going to hit the top. So as a consequence, I do get an image on the screen. And it turns out, if you have a pinhole that's small enough, you can make a decent image. And any lens, you can improve its performance by taking it and putting an aperture in front of it, which is tiny. So in an actual camera where you have a lens, if you have an aperture in front of it that's tiny, you get an additional kind of like pinhole focusing from the aperture, and that gets you crisper images and a greater depth of field. This principle of just being able to have a pinhole camera has been, you can use to make what's called a camera obscura, and that's this. You can have a light-proof box with a hole in it, and you can see an image of the outside world. This is one which is actually in an art museum, and they took a whole room and they painted it white, but they covered up all the possible light sources and turned off the lights, and there's a hole in the far wall. What you see is an image of what's outside the room on the wall. This is a camera obscura that you can step into. It's a very, very cool thing. And it turns out the simplest eyes in nature work this way. If you look at a Nautilus, its eye, there is no lens in its eye. It's just an opening. It's a pinhole opening. And so you get an image back here on its retina. Crazy. And so a Nautilus has an eye that works like this. It is open to the ocean. Yours is a little bit more complicated. To make better images, you can collect a lot more light if you use a lens, because rather than having a tiny, tiny hole which lets in only a tiny amount of light, you can have a big lens which lets in lots of light, and it collects light and makes an image on film or an electronic detector. And we put in an old school one with film just because we're old school. If you see the pictures of us in the front of the book, yeah, we were all born long before there were digital cameras, and so we got a film camera here. Rays of light get collected and then appear on film or an electronic detector. Now let's take a look at a lens problem, but we're going to do it in the context of a camera. So suppose I have this situation. I have a 35mm film camera, and the image of a woman appears 15 millimeters high on the film. She is 1.5 meters tall. when the picture was taken, the lens was 50 millimeters from the film. And the question is this: how far is the woman from the camera? I want you to stop the video right here, and I want you to think, how do you set up this problem? Now let's start by remembering we're going to use these relationships here because these are our relationships for lenses. So we just have to figure out what the different parameters in the problem corresponds to here. Now, S is the distance of the woman from the lens. That's the distance of the object from the lens. So S is what we're looking for, okay? S prime is the distance of the lens from the film, and we're told that's 50 millimeters. And I'm going to go ahead and put things in meters, so 0.050 meters. That's what S prime is. I'm also given some numbers here. I'm given how high the woman is, how tall she is, and how tall her image is. Those are my H and H prime values. H is equal to 1.5 meters. That's her height. H prime, that's the height of the image. That's 15 millimeters, so 0.015 meters. Now what I want you to do next is to think about how do we proceed from here. We've got two basic relationships. Which one do I want to start with? Oh yeah, you should be pausing the video and thinking about that. Don't just wait for me to tell you, you little scamp, which relationship should we start with? And really, we've got this first one here, 1 over S plus 1 over S prime is equal to 1 over F. I'm not going to do that because I don't know the focal length of the lens, and I don't know S. So this one's not that useful, but check out the second one. The second one has got H, H prime, S, and S prime, and those are the variables that I'm working with over here. So basically, I can just say this: how far is the woman from the camera? That's S. That's what I'm looking for, and I know S prime, I know H, and I know H prime. I can put those together and I can solve for it. I want to mention something here. Over here, I wrote H prime is equal to 0.015 meters. But in fact, it's a real image on the film, so this really should be negative 0.15 meters because her image will be upside down on the film, but then you just take the film and you turn it right side up, so we don't have to worry about that. So if you're solving a problem like that and you end up with an extra negative sign, in this case, if it's the magnification, I cannot worry about it. The negative sign is just a signifier. It says the image is upside down. I can just do the magnitudes, and if I do that, what I get is this. I get that S is 5 meters, so she is 5 meters from the camera, okay? And that seems reasonable. That's like 15 feet, and if you're taking a picture of someone and you're gonna get their whole body in, that's not an unreasonable distance. The next step, I want to do another camera problem, and this is kind of a conceptual one, but we're going to reason using the equations. If you see a person taking an image with a camera with a lens that sticks out like this, the lens is way out here. It's way the heck in front of the detector, which is way back here. Why would I want to have this giant value of S prime? Why do I want to have the lens so far in front of the camera? Why is that important for a so-called telephoto lens? Why do you want that to be true? I want you to think about the relationships and what they mean and what they're telling us. Take a minute to reason. I'll be back. Well, when you use a telephoto lens, what you're trying to do is you're trying to make the image be really, really big. So let's suppose you're on a safari and you're taking a picture of a lion, and I want my image of the lion, my H prime, to be really, really big. Okay? Now I'm going to rewrite the equation, this equation right here, with H prime and then the other variables. So H prime is equal to H times S prime over S. And I've left out the negative sign. The negative sign just tells us the image is upside down. So I want to have a really, really big image of a lion. Here's my options. 1, I can pick a really large value of H. I can pick a really, really gigantic lion. That would work. That would work. Or I can make S really, really small. I can get really, really close to the lion. But if you can't find a gigantic lion and you'd rather not get close to it, your other option is to make S prime really big. In other words, take the lens and make the lens be really far from the detector. And I have a camera that has a zoom lens on it, and when I put a zoom lens on it, it's just the lens, the camera sends the lens further out. My lens sticks further and further out the front of my camera. And that has to be true because I have to make S prime big in order to make H prime big. Now I want to take a look at another conceptual question. I want to think about a fire starter. Okay, I don't know if you've ever done this before, but I certainly have. You can use a lens to start a fire. Oh, this is going to be part of our story of Piggy. Here's a question. Do I want a lens with a short focal length or a lens with a long focal length? What would be better for a fire starter? Okay, and then I want you to explain your results. So think about what you want. Take a minute, reason, I'll be back. Now let's take a look at our basic relationships that we have right here. Okay, and I want to have a fire starter. What you're doing with a lens is you're using a lens and you're actually projecting an image of the distant sun. So I got the distant sun out here. And I'm projecting an image of the sun on a piece of wood or something that I want to set on fire. That's what's happening. The rays of light are coming together and I'm making an image of the sun. And I want to have a really, really tiny image. I want to have S prime be small because I want the image of the sun small. Because the smaller the image is, the more concentrated the light will be. If I make the image big, the light is spread out. That's not what I want. So I want tiny values of S prime. So now let's look at this top relationship right here. Okay, 1 over S plus 1 over S prime is equal to 1 over F. Now first off, let's think about this. S is the object distance. That's the distance to the sun. That's a huge number, and 1 over a huge number is basically 0. So this number basically goes away. And so what I see, my relationship reduces to this. 1 over S prime is equal to F, or S prime is just equal to F. And that's really true. If you take a lens and you make an image of the sun, the image basically appears at the focal point. I mean, that has to be true. That has to be true. So if I want S prime to be really, really tiny, I need the focal point to be really tiny as well. And so I want a very, very short focal length lens. I'll mention as well, I'm making a real image of the sun. This has to be real. So as a consequence, what type of lens do I need? I need a converging lens. And this is going to be important to the story, which we're going to tell about Piggy on Friday. Now I want to talk about how your eye works, okay? And this is kind of a simplified model of the eye. And we've talked about the fact that in physics, we're going to take these very complicated biological systems and we're going to reduce them to the kind of like the simplest possible model to be able to understand it. And understand the optics of your eye, we have basically this. Rays of light come in and they're focused by a structure that's a mix of your cornea plus the lens in your eye. And they come to a focus on your retina. That's our image. That's our model of the eye. Now I just want to think about the camera for a minute. If you have a camera and you're focusing it on objects at different distances, if S changes, you can't change F. F is the focal length of the lens, and that's fixed. If I have a 50 millimeter lens on an SLR camera, the focal length is just 50 millimeters. That number does not change. And so I change the focus. If I'm looking at objects at different values of S, I have to change S prime, and so I adjust this. And so I focus a camera by moving the lens closer or farther away from the detector. I change the values of S prime. That is not, in fact, the way your eyes worked. If it did, if you're trying to look at a close object, you would have to increase the value of S prime. You would have to make the lens further from the retina. Your eyes would have to bulge out like this, and that would be awesome. I would like to live in that world, but that's not the way it works. The way it works is this. If you look at your eye, the distance between the lens and the retina that's that distance s prime. That is fixed, okay? And we're going to assume it's 0.017 meters, which means 1 over s prime is about 60. That number is fixed. You're going to be focusing on objects at different distances s, and so what you'll do is you're going to change the focal length of the imaging system of your eye. It's going to be variable. So when we're working with the eye, we're going to take the basic relationship that we have for lenses, which is this: 1 over f is equal to 1 over s plus 1 over s prime, and it turns into this: 1 over f, 1 over the focal length, is equal to 1 over s prime, which is just 60 plus 1 over s. And if I have if I have different distances, I have to have different focal lengths. And that is the way that your eye will focus on different things. The process of changing the focal length of your vision we call accommodation. If you're focused on a distant object, your ciliary muscles are relaxed, your lens is nice and relaxed and it's thin, the power of your visual system is 60. And because remember this, our basic relationship is this: 1 over f is equal to 60 plus 1 over s. Well, remember, 1 over f, that's the power of your visual system. That's the power. So the power of your visual system, if I'm looking at a distant object, s is equal to infinity. 1 over infinity is 0. This term goes away. The power is 60. For close vision, your ciliary muscles contract, and then you have your lens in your eye gets chubbier, and the focal length gets shorter, and as a consequence, the power goes up. And the power of your lens will be the power that it starts with, which is 60 plus the degree of accommodation, okay? And so to look at something which isn't at infinity, I'm going to change the power of the lens in your eye. Now let's look at some numbers. If I take this basic relationship right here, and I say 1 over f is equal to 60 plus 1 over s. 1 over f is the power of your visual system. We can compute what the power is to see at different distances. By the way, I'll mention the stuff I'm doing, this is an approximation. 1 over s prime, it's going to vary. It could be approximately 60, but it could be slightly different than that. It turns out for the calculations that we'll do with vision, it doesn't matter. This is an approximation, but as an approximation that is completely justified. We can just say 1 over s prime is 60, and that's fine. So we will do that going forward. If I'm focused on an object at infinity, 1 over s prime is equal to, or 1 over s is equal to 1 over infinity. It's just 0. So I get a power of 60. If I'm looking at an object at 1 meter, it's a power of 61. Object at a distance of 0.5 meters, it's a power of 62. 0.25 meters, I need a power of 64. So you can see the power increases as I'm looking at objects that are moving closer and closer and closer. And that is how you focus on close objects. But there is a limit. There is a limit, and you just can't focus on objects closer than that. And if you look at this picture, you can see that distant objects, these daffodils out here, are in focus, but the close objects are not. They're closer than the near point. And what I want you to do is this. I want you to measure your own near point. So what I want you to do is I want you to take something which has got some detail in it, like writing on a piece of paper, and I want you to see how close can you hold it and still have it be in focus. So far away, it's in focus. Bring it closer, 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 closer. Keep it here, closer, closer, closer. Keep your glasses on when you're doing this. Closer, closer, closer. What is your near point? And I want you to measure approximately what that is in centimeters. Take a minute and measure. I'll be back. Now, if you ask me to do it, my near point is about 1 meter, and I actually did this. I'm in the room where I make these videos, and I took this card and I wrote something on it, and I looked through my glasses. I'm looking through the top for reasons I'll talk about, and I saw how close can the object be, and I can keep it in focus. And it turns out it's about 1 meter away. My near point is approximately 1 meter. Which is kind of crazy. And you likely ended up with a number which was much less. A typical number that I'm seeing people in the class get, these days is about 10 centimeters. So your near point is 10 centimeters. For me, it's a meter. And what that means is if my near point is a meter, I can't focus on anything closer than a meter. That does not work. I need vision correction, and I have vision correction. And exactly how that works, I'll talk about in the next class. But I want to think about this. Now let's do the first of our vision calculations. I'm going to ask you this. So people in the early 20s, like people like you, have about 10 diopters of accommodation. So my question is, given this, what is the near point of your vision apt to be? Take a minute, think about how you'll solve that problem. I'll be back. And let's go ahead and get started. We're going to use this basic relationship right here. This is the one we use for all of our vision calculations. And remember what the different terms refer to. This is the power of your visual system, okay? This is the distance of the object that you're looking at. Now, if you're looking at a distant object, so suppose you're looking at s is equal to infinity, that tells me that for a distant object you use the smallest possible power and you get a power of 60, because 60 is equal to 60 plus 1 over infinity, and 1 over infinity is 0. So you get a power of 60. That's for your far point. That's your distance vision. But if you're trying to look at something near, what you need to do is you need to increase this power. You need to increase this power. And at your near point, the power that you have is your power of your relaxed vision, which is, we're assuming to be 60, plus your 10 diopters of accommodation. So your power at your near point is going to be 70. And if the power is 70, what does it imply for your near point? Take a minute to continue. I'll be back. Well, the way we calculate it is this. The near point is a distance. That is how far away is the object that I'm looking at. If the power of my visual system is 70, what is s in this equation? Because I've put in the value for the power. And the power of the visual system, if it's 70, I get a distance of 0.10 meters or 10 centimeters. And that, my assessment is that seems about right, because that is in fact what we calculated for you, or you estimated for you. Likely estimated a distance that was approximately 10 centimeters. So this makes sense. Now remember, if you take two lenses and you put them in close proximity, you add their powers to get a total power. Okay? And we did something like this earlier. I just want to remind you about that. And that's how a magnifier works. So if you look at a magnifier, what you're doing is you're taking a converging lens and you put it right in front of your eye, and the power of the lens adds to the power of your eye. And if you have more power, that allows you to see something closer. And let's do a quick calculation to see how that's true. So a person with a near point of 10 centimeters uses a magnifying glass with a focal length of 5 centimeters. What is the new near point? Now remember, we're going to start using this relationship. 1 over f, that's the power of your visual system. And let's just think about that not as 1 over f, but think about it as the power, is equal to 60 plus 1 over s. Think about how you'll set up and solve this problem. Take a moment. I'll be back. Well, 1 over f is the power of the visual system, and the person has a near point of 10 centimeters. So first off, I'm going to do this. I'm going to look at the person's near point. At the near point, the power of the visual system, which is 1 over f, is equal to 60 plus 1 over s, and I've got to put that in meters because I want powers in diopters. So I have 0.10 meters. I get a power of 70 diopters. Okay? That's at the near point. But I stick in front of that a magnifying glass with a focal length of 5 centimeters. Well, the power of the magnifying glass is 1 over f, 1 over 0.05 meters. And remember, since I want a power in diopters, distances have to be in meters, is 20 diopters. So I take my 70 diopters of my near point, and to it I add 20 diopters. And if I take two lenses and stick them next to each other, the total power is just the sum of these two. So I have a total imaging system with a power of 90 diopters. So the next question is this: what is the new near point if the power of the visual system was not a puny 70, but it was a breathtakingly awesome 90? What would the near point be? And I use the same relationship to calculate. I take 90, well, that was a 60, that's not right. I take 90 is equal to 60 plus 1 over s, and I calculate what is the value of s. What is the value of s? And what you get is a distance of about 3.3 centimeters. 3.3 centimeters if the lens for the magnifying glass as given. And so instead of being able to see something 10 centimeters away, I can see it 3.3 centimeters away. So it doesn't actually magnify. It doesn't actually magnify. What it allows you to do is it lets you get closer. Instead of looking at it from 10 centimeters away, I'm looking at it for 3 centimeters away and thinking about our basic relationship. For the h prime over h is equal to negative s prime over s. S prime is fixed. If s prime gets smaller, h prime is going to get bigger. The image on your retina will get larger. And so I don't really magnify it. I'm just allowed to get closer to it. And if it's closer, it's just going to make a bigger image. And so I'll be able to see it more clearly. This is our first example of a vision modification, is using a magnifier. But we're going to talk about a whole lot next time. Because next time we're going to talk about vision correction, or as I like to call it, I like to talk about it as we're thinking about the differently visioned. Not that we have vision defects. Oh, no. We are just differently visioned, and we will talk about that next time.